Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we solved one numerical problem. So, today numerical problem on torsion, and today we will be taking another numerical problem on torsion. Okay. So, let's write down that problem. So, problem 2. Okay. The problem says a couple of 70 Newton meter is applied to a 25 millimeter dia 20240 aluminum alloy shaft as shown in figure. Okay. So, I will draw the figure later on. The ends A and C of the shaft are built in and prevented from rotating. Determine the angle through which the center cross section O of the shaft rotates. Given your G shear modulus value is 26.5 giganewton per meter square. Okay. So, let me draw the figure, then I will explain. this is the problem. Okay, a couple of 70 Newton meter is applied to a 25 millimeter diameter 20424 okay, aluminum alloy shaft. So, this is the shaft. Okay, this is the shaft. At this point, at point B actually you are applying 70 Newton meter couple, okay, as shown in the figure. The ends A and C of the shaft are built in. Okay. So, they are clamped, okay, they are built in, okay, in the with the support and prevented from rotating. So, it cannot rotate actually. Okay. So, if you try to rotate, because when the torque is applied, okay, it cannot rotate at the end. So, the rotation is completely prevented or restricted at A and C. Okay. So, determine the angle through which the center cross section O. So, O is the center part of the shaft, because the total length is 2.4 meter, the shaft length is 2.4 meter, this is 1.2 meter. So, center of the shaft, though it is not looking, I hope that you are understanding, it is not to the scale. So, O is the center portion of the shaft. Okay. You need to find out the angle through which the center cross section O of the shaft rotates. Okay. The twist angle at O you need to find out. So, G, that is shear modulus, is given as 26.5 giganewton per meter square. Now, how to solve this problem? How to proceed with this problem? So, if you look at this problem, if you try to draw the free body diagram, okay, of the shaft. So, if you try to draw the free body diagram of the shaft, then basically this is the shaft, this is the whole shaft. Okay. So, it is rigidly built in the support. So, therefore, rotation is restricted. So, you will be getting, or the some moment reaction will be getting developed. So, that is nothing but say MC, which is not known to me, that is a support reaction. Okay. And at point B, you have a moment MB, that is equal to 70 Newton meter. Okay. And similarly, at support A you will be having a moment due to the reaction at the support, okay, and that is nothing but MA. Now, if you look at this free body diagram of the shaft, this is your free body diagram of the shaft. Can you solve, because how many unknowns are there? Two unknowns, MA and MC, both are unknown, right. So, can you determine those two unknown moments, MA and MC? You cannot. Why? Because this is the indeterminate structure. So, how many equations available with you as per your equation, equilibrium equation? Because there is no force. So, those summation of Fx, summation of Fy, all those things are not coming to the picture. Okay. So, only summation of moment equal to 0, only one equation is available with you, one equilibrium equation is available with you, that is summation of moment equal to 0. Now, summation of all moments equal to 0 you can apply, but you have two unknowns, only one equation is with you. So, therefore, you cannot solve it. So, this is a classical example of statically indeterminate structure. So, therefore, if I want to solve it, then I need to impose some geometric compatibility, then only I can solve it, as I told you, okay, previously. Okay. So, now if I try to draw the free body diagram of the part AB and BC separately, and let us see how we can get the free body diagram, and from there whether we are getting some clue or not. Okay. So, we are going to draw the free body diagram of three sections of the shaft. So, free body diagram of 3 sections of the shaft. Now, we are going to do that. Okay. So, first one is this is the first part. First part means AB part. So, the part which is on the left side of this wheel, okay, we are separating out that part, and this is the free body diagram, because MA is anyway is acting at this end. So, therefore, it is this shaft is under torsion or the twisting moment. So, if I cut the shaft at point B, okay, and if I consider the left side of the shaft, whatever we did for the bending moment calculation and shear force calculation, then basically this is the moment is acting at point A. Okay. So, this is your point A. So, therefore, to balance this, you should have the same amount of moment MA at this point B, and therefore, you are getting some twist compared to this point A. Okay. This is the twist phi BA, agreed. So, this is the twist over this whole length phi BA. Then I can draw the free body diagram of this wheel. MC, this is at B, some torque, some couple is acting 70 Newton meter, okay, that is externally applied couple. This is your MA. Okay. So, this is the free body diagram of that wheel on which the couple is acting. Okay. Then the next part is from B to C. Okay. From B to C, right, that is another part of the shaft. Okay. So, let us draw that. So, from B to C, this is MC. Okay. This is MC, okay, and this is the point O, which is our point of interest. This is B, this is C, okay, and you are getting the twist over the whole length at O. This is the twist, say phi OC. And this is the twist you are getting at this end, say that is phi BC. Okay, absolutely fine. Now, still I do not know MA, MC and all those things, right. If we apply the geometric compatibility, then only we will be coming to, or we will be getting some clue. Let us see how we can get all those clues. But at this moment, I have what I have done. I have drawn all the part, I mean free body diagram for the all the parts of the shaft, whatever I have shown or whatever I have in the actual problem. Okay. So, now if I try to solve, now satisfying your moment equilibrium, satisfying the moment equilibrium, okay, we can simply write MA plus MC minus 70 equal to 0 as per this figure. Okay, as per this figure I can write this, and where MA and MC both are unknown to me. Okay, and this can be further written as MA plus MC is equal to 70, which is equal equation 1. Okay. Now coming to the geometric compatibility. What is the possible geometric compatibility, what you can think of? Now if you go back to the actual figure, basically that wheel is the connector between these two parts, part BC and part AB, both are getting connected through this wheel, yes or no? Yes. Now therefore I can say that whatever twist you are getting at this point B of this shaft, okay, the same amount of twist you must get at point B of this part of shaft, right, to satisfy the continuity. So phi BC must be equal to phi BA, isn't it? So continuity of the shaft, and without that clue actually you cannot proceed, because this is an indeterminate structure, you cannot go ahead. So continuity of the shaft at the point B requires that phi BC equal to phi BA. So equation 2. Agreed? So this is the biggest clue or the biggest information we have extracted from the problem. Okay. So now your load deformation relation, from the load deformation relation whatever we have derived earlier, we can write phi BA is equal to MA LAB GIZ. Can I write that? Yes, of course I can write it. That is the expression for angle of twist, right, over the length LAB, that already we have derived, right. Similarly, I can write phi BC is equal to MC LBC by GIZ. Okay. Similarly, I can write phi OC is equal to MC LOC by GIZ. Agreed? So these are the expressions of twist at different locations of the shaft, phi BA, phi BC, phi OC over the length of your concern. Okay. So this is a equation say 3. Now solving equations 1, 2 and 3, you will be getting, because already you have seen in equation 2 that is phi BC is equal to phi BA, right, as per your geometric compatibility. So I can simply write MA LAB GIZ is equal to MC LBC GIZ, because same material, same cross section of the shaft, so GIZ will be remaining same. So from this I can get MA, okay, LAB minus MC LBC is equal to 0, and that is my equation say 4. So, LAB and LBC both are known to me, yes or no? Yes, of course. LAB is given as 0.6 meter and LBC probably LBC was 1.8 meter. So, that is known to me. So, now I have got two equations. This equation, this is the relation between MA and MC, and another equation, if you recall the equation 1, that is also MA and MC. So, these two equations basically can be solved, and from those two equations we can get the magnitude of MA and MC. Okay. So, let us do that. So, I am rubbing this figure. So, solving equations 1 and 4, okay, we will be getting MA equal to 52.5 Newton meter and MC is equal to 17.5 Newton meter. Okay. So, two unknowns now are found out. So, unknowns were MA and MC. Now, we have found out those two unknowns, and now once you have found out these unknowns actually, then you can find out phi OC, because that is, this is your basically objective, right, phi OC. So, to obtain phi OC, now you have got MC, you know LOC, G is given, IZZ you can calculate because the cross section of the shaft is given. So, IZZ, let us calculate IZZ, IZ rather phi pi by 32 into 0.25 to the power 4, right. So, that is your IZ, because the shaft diameter is given. So, that is your IZ, okay, and G is given 26.5 giganewton per meter square. Therefore, phi OC is equal to 17.5, that is MC value, into LOC, that is 1.2 meter, okay, 26.5 into 10 to the power 9, that is the G value in terms of Newton per meter square, into IZ pi by 32.025 to the power 4, okay, radian. So, that will come as 0.021 radian, that is nothing but 1.2 degree. Okay. So, this is the twist at the central cross section of the shaft. Okay. I hope you have understood that how we have analyzed this problem, and this kind of problem should be analyzed like that. Okay. Any indeterminate problem you cannot solve directly by using your equation of equilibrium. So, what you have to do? You have to find out, or you have to extract the information about the geometric compatibility. So, once you have picked up the geometric compatibility, then rest of the problems will be pretty straightforward. Okay. So, I will stop here today. So, in the next lecture we will be starting the new chapter, and then basically we will move on with the discussion with I mean, now remaining part is nothing but your bending and shear stress, deflection, and finally stability. Okay. So, these are three topics are remaining. So, we will be looking at those topics gradually. Thank you very much.